Let's continue from last time. Last time what we did in the area moment of inertia, we actually did only two things, right? We actually calculated from the definition, the integration basically. Then we learned how to cope with it with the parallel axis theorem. Today, we will talk about something called composite material. Okay, and then we will go to product of inertia, and hopefully we could go to inclined axis within an hour. Okay, and then of course the assignment will be following the class as such. Let's see how quickly can we go. Okay, so let's start the new topic for today, the composite area. Let's discuss first what it is. Okay, this composite area is just a big area that is comprised of more than two areas. Well, two areas or more. Okay, usually it means that it's the area that we know how we calculate the I, right? And then we have to calculate the I for the whole area together. Okay. In that case, the way we analyze it, we will actually define all components first, then using parallel axis theorem to actually combine to find out the small areas moment of inertia depending on which axis. Then we know through its own centroid, then we can move the axis to the common axis, right? And then we combine or will subtract the value to get the summation of all of them, of the total area. So that's the concept. So in essence, in this part there is no new theory yet, right? It's something that we already know, right? We just, rather than having to cope with one area, now it's a bigger area that is made out of two areas or more. Okay, let's see some example. Again, these notes are on the website already. Hopefully you have seen it already. Let's say we have this composite area. Okay, this is the area, and apparently we have to find the area moment of inertia about x axis and y axis. Okay, this xy axis is sit on the centroid of the total area, not this area, not that area, the total area. Okay, in this case, because there is no symmetry for this area, of course we will have to find the centroid first. Okay, so we go through step by step. First we identify the areas, and then we define the centroid, and then we find the area moment of inertia. Right, as we discussed last time, for this example I will only show Ix, not Iy. Okay, but the system, the idea will be the same. Let's talk about what do I mean by summation or subtraction. Okay, we can separate these two areas into that piece, that small piece there, right? Then we calculate Ix, then another piece is that piece there. Then we calculate Ix and then combine them. Okay, that's the concept of summation, or sometimes it's called addition. Okay, or we could look at subtraction. It could be either way, meaning that circle, that rectangle is the big rectangle, the whole thing here. Okay, we can find Ix for the whole of the rectangle. Then that one signifies the whole here. The whole here is also rectangle, right? So we can find Ix of that. You notice that axis is on the top right of the whole, right? And that signifies it. So basically we can also find the Ix for the whole, and then the total Ix will be that one minus that one. Okay? So it depends on how we view it. We can use positive addition, summation, or we use negative. Okay, each case, in this case it will be the same difficulty, the same simplicity, the same amount, but some picture will be better doing subtraction, and some picture will be better doing addition. Okay, not this one is the same, still two areas. Okay, so let's see how we go through the calculation. As I said, because the question doesn't give you the centroid position, then we have to find it. Okay? Now, because I already gonna calculate the Ix, all I need is the position in Y. Basically Y bar, not X bar. Okay, because our measurement will be in Y. Right, Ix equal to Ix prime bar plus A dy squared. Remember that one? Okay, so let's find. The area 1, simply calculate, just rectangle. The height times the base, right? 10 times 40. Area 2, rectangle, just calculate it. We know the position of the centroid. A1 sit here, right, on the top. The centroid is here, half width. I will measure everything from bottom here. Okay? Therefore, in this case, Y bar 1 will be 35 centimeter. Y bar 2 belongs to A to Y curve, Y curve 2 is 20 centimeter. And this is what we call Y bar for the central centroid, right? Using the summation form, there. Total area times Y bar equal to A1 times Y curve 1, A2 times Y curve 2. That's all. Calculate Y bar, then we get Y bar, 25 centimeters in this case. Okay? So, now identify according to, let's say summation, that one. Okay? We talked about the concept already. So, we'll find Ix of A1, Ix for A2. Okay? And then combine them. Now, this is rectangle. These two are rectangle. We have proved the formulation for Ix and Iy that go through its own axis, right? So we're going to use that. In this case, Ix prime will be BH cubed over 12. Okay, we proved that in example 1, I think. Okay? And using that equation, then we can find Ix1, quite simply. BH cubed over 12 plus A time distance between the centroid, that one, and the centroid of the local one. Okay? Where is that 10 coming from? Can I go back a little bit? That one from here to here is 35, correct? We calculate Y bar 25. Therefore, distance between these two axes and there must be 10. Correct? Since we talk about that one, maybe we talk about this one too. From here to here 25, from here to here then has to be 5. Right? Correct? Okay? So put in the right equation. That one go there 10, then calculate it. That one 5, therefore that equation. Okay? Now notice that Ix is going through that axis, not that axis anymore. Correct? That Ix also goes through that axis and that axis is the same axis. Right? Therefore now you can combine them. There we are. Okay? So extend the knowledge from last time to do it, that's all. Did I show subtraction as well? Yeah. What about subtraction then? Okay? The centroid doesn't change because you change the concept. The centroid and control are in the same place. So I'm not really calculating that. I'm going to use that knowledge. Okay? Remember Y bar? Y bar is from here to here, right? 25 centimeters. That height is of course 20. Therefore the gap is 5. Right? That's the big picture. That is the hole. The hole is only 30. Therefore the height from here to here is 15. Right? From here to here 25, so 10 left. Okay? You can also calculate A3. A3 is 40 times 60. A4 is 30 times 40. Right? Rectangle, normal rectangle. Again, using the parallel axis theorem, we can calculate A3 about this axis. Right? BH cubed over 12 times A D squared. Right? For A4, the same idea. BH cubed over 12, area times the distance squared. Okay? Then you get it. Then this time you don't combine them, you subtract them, remember? Right? Then that one minus that one, you have the same answer. Okay? Just for example. That one is already on the website, right? Okay, so that is the concept of the composite area. It doesn't matter, you have 10 area, then you calculate one by one, and then you move the axis, right? And then combine them all or subtract them all, depending on the case. Okay? Could it be any simpler? No, it couldn't. Okay? Now, go to the next topic. This one here, by its own use, not much. Okay? However, we need it for some other calculation. Okay? So we have to be able to find it anyway. Okay? This is called product of inertia for an area. The concept is just xy times dA. Okay? Not ix. Ix is y squared dA. Iy is x squared dA. This is xy. Right? The combination of them. Now, because of this, then the positive, negative become having some meaning. Okay? Last time x squared, no matter which way you take, minus then x squared it become plus. Okay? So this time the positive, negative has meaning. Meaning if you actually have certain symmetry about x or y axis, the ixy will be 0 automatically. This is the idea. Okay? That picture has symmetry about x-axis. Notice that every dA on the top of the x will have a pair of dA below x. On the top it will times y, at the bottom times minus y. When you combine it becomes 0. Right? So if it has symmetry about one axis, x or y, that you are taking about, okay, it has to be axis that you are taking about. Okay? If I set x here, then that one doesn't have symmetry. Right? It has to be on the symmetry line too. To be more that one. Okay? If it symmetry about y, that will have minus and that will be plus. Right? Because this one is minus x, that one is plus x per se. Right? And similar, once you have symmetry, your ixy will be 0. If you don't, then, well, sorry for the mobile phone, I forgot to take the volume off. Okay? And usually, in terms of integration, we will take that advantage. Okay? Should I continue? Okay. The parallel axis theorem for the product of inertia. Where's my watch? Okay. Similar. Let's assume certain thing. This is similar to what we have done for Ix. Okay. The idea will be the same. Let's say we know the centroid. We know the Ixy about x prime y prime, which we will call Ix prime y prime bar. Okay? Again, it is the product of inertia about with respect to axis that goes through the centroid. Okay? Of course, by the definition, it will be x prime y prime dA. Okay? So, distance between axes, we should know it. So we'll find again similar. If we know with respect to x prime y prime, now we want to know how do we use it to calculate with respect to xy. Okay? So this is the definition from xy. Okay? X is equal to dx plus x prime. Correct? Y is measured from here to here, then dy plus y prime substituted in. Okay? We can't do anything much about it in this form, so we expand the term into 4 terms. And then we deal with it one by one. Okay? Starting from that one, okay, the first term, d subscript x, d subscript y constant. So we take it out of the integration and integrate dA, it's just total area, right? Nothing complex there. Then the second term, we can take dz out, dx out, right? D subscript x out. Then we left with y dash dA. Again, that integration is the format we use to find centroid. Integrate y curve dA equal to y bar integrate dA, right? So we change that term into that. Now notice the prime here and the prime here. It signifies the fact that this is not relative to xy. This is relative to x prime y prime, right? Therefore, that will be the measurements in the y direction, the distance between x prime and the centroid. But because x prime is on the centroid, therefore y bar dash doesn't exist or 0. So that term, the whole term becomes 0. Okay? The third term, similar pattern, we'll take dy out. That one is the expression to find x bar. In this time it means x bar in x prime y prime axis, right? Again, because y sitting on the centroid, the measurement of x bar prime is 0. That one also disappears. The last term, that term, is in fact that definition, right? Therefore, it is a term that we assume that we know. And then we have that form of parallel axis theorem for product of inertia. Gonna move on then. Example 5. Continuing from last time, example 4, right? That one there, we want to find the IXY with respect to x and y. Before we go forward, this picture does not have symmetry about x or y. It has symmetry about this line in a half height, yes, but that's not x. X is down here, right? It has symmetry on the line at the half width. Again, it is that line, not y. Y is here. So this rectangle do not have symmetry neither about x nor y. Okay? So how do we do it? If we do this one, small dA, and integrate it, don't forget this time we time x times y inside the integration, correct? So that element must have one x value and one y value. In that case, if we're gonna do that, we can, but we have to integrate twice. Okay? Once with respect to x, one with respect to y. As I said, we take the advantage of the symmetry. So, if I shoot a strip that way, okay, that small strip will have a centroid in the middle of it, right? And then I will set up a sub, not the real axis that we calculate, new axis, x prime, y prime on the centroid. Now, don't forget this time now, this red element is symmetry about this y prime axis, is also symmetry about this x prime axis, correct? Therefore, the I bar x prime y prime is 0. Okay? So we have to care only for the second term, this term here. Right? Okay? dA, by the way, I said it, is b times dy, right? Normal dA. That one, the d in front, actually just means that it forms small element. Okay? That one is dA, b dy. D subscript x is the measurement in the x-axis. Therefore, it measures from here to here. Correct? Therefore, it is minus at the centroid, that is b over 2. Therefore, it's moving this way, minus b over 2. Okay? Then that one is distance between the two axes of y prime and x prime and x. So measure downward here minus what we call here is y, right? Then into that form, integrate it, and that's it. Just in case you wonder, can you set the strip in the vertical using the same theory, using the same technique? Yes, you can. Okay, but integration this time will not be dy, will be dx. That's all. Okay, but the idea will be the same. Okay, that it is not very logical to study about product of inertia without thinking about what we're going to use it for. Okay, well, that's the answer. Oh, the composite area for the IXY. Okay, the same IXY we want, that one, right? Last time we done IX already. This time you'll see the product of inertia, IXY. Let's just change the question. Then we want the product of inertia with respect to XY axis. Centroid, we already find it. Or apparently, since we are talking about subtraction, we also can find centroid with the subtraction idea. It doesn't have to be combination all the time. Okay? So this time, I just try to find centroid using the subtraction idea. Okay? Again, we will have one big picture and one whole to minus off. Okay? There. A3 we calculated before, A4 well, simple calculation, so I'm not repeating myself. Okay? The concept, this centroid here is 20, this one here is 30. Correct? The centroid of the area. From here to here 15, from here to here 20. Notice I still set the measurement from the same axis. That axis will be on the left and on bottom of the whole picture. Okay? Of the total picture, not the sub picture. So there we are. Then I will have x bar rather than positive this time, because by concept we have minus. Okay? Therefore, if that one is 24, this is x bar, so area A3 times 30 is that term. And then minus area A4 times 20, that term. Okay? Y bar will be similar idea. Okay? Y curve times that area and y minus y curve times that area. 2400 times 20 and then 1200 times 15 minus. Calculation, that one is new, but that one you should notice that it is the same. Okay? Again, which one should you use? It depends on situation. In some, this one will be the same difficulty because there can be only two areas. Okay, sometimes you have to decide, but that's probably for the later stage. Then find IXY. Again, this is we gonna calculate use about this axis at the centroid, right? We already measure from here to here 25. That is 20. So we have 5 left. From here to here is 40. Right, x bar 40 from last page. From here to here 30, so the gap here is 10. Okay, that's for the big picture. For the whole, again from here to here 25, y bar. Right, from here to here half height 15, so 10 left. From here to here 40, from here to here 20, so 20 left. Okay, then there we go. That one is for area 3. Okay? When you measure from that axis, it's measured downward. So if that is minus 5, measure to the left, minus 10. Right? Because to the right positive and up positive, you measure against it, so it becomes minus. Okay? That one is the same idea. If it against the axis, you say positive, then it becomes negative. Okay? And then you have the 2. Then Again, that one minus that one, in this picture, it turns out minus. Again, now, because it's not x squared or y squared, it's x times y. Therefore, there is no guarantee that it will always be positive. Ix, Iy has to be positive, right? Because it's x squared, y squared. dA is always positive area. Okay? The next one, I will try to go. This is just putting ideas into practice. The next one will be huge amount, well, certain complexity improved. So I will try to go slowly. That one, I just show it as a summation form. The same idea apply. Okay? And the same result as well. But this one, that area and that area combined. That one is minus 80, minus 40 combined to minus 120 like last time. Okay? It will give you the same answer. But since we are here, from here to here is 10 centimeter. Notice that measurement, now it becomes positive. Okay? From here to here is, well, that one is 40, that one is 10. So that 10, this time become positive as well, because it's going to the right. Okay? Now, we're going to go this one. This one here, apparently, for something that is not really nice, apparently, they recognize something. Don't forget, this is about how the area resists moment. From time to time, although you apply moment about that axis, when the member bend, it doesn't bend according to the moment, it bend in an angle. Okay? So they realize there must be certain axis that control this bending, that rotation of the area, not the moment itself. So they work out and they find that it's about the incline axis that they have to find out. Okay? So this is the way they set up. We have xy. Okay? Let's assume that we know ix, we know iy, and we know ixy. Okay? We want to know now what happens if we move the axis, rotate the axis around. Okay? Just to avoid confusion, they call that axis that rotates u and v. It's just x and y rotate. Once it rotates, it becomes u and v. But it's still the same axis xy that keep moving. Okay? The measurement of the motion is theta. Okay? And they keep moving in a circle. Now, if we go for first definition, here the assumption, as I said, the area moment of inertia about x and y are known, ix, iy. Okay? And the product also known, ixy also known, which by now we can calculate. We see the example already. Then that one. By definition, right, ix is y squared dA because x and y are 90 degrees. Okay? In this case, u and v are 90 degrees. So iu is v squared dA and iv is u squared dA. Okay? And of course, iuv is uv dA. Now what happened is they will try to link the uv and the xy right now. The same way we used to link x prime, y prime and xy before we start doing anything, right? This is the same thing. They try to link uv and xy. Okay? Notice that that is called u. Okay? The triangle that we should look at is this triangle. From this point to that point, we call it y. Right? Correct? Then, if we look at this triangle, this 90 degree triangle, okay? This is theta, this is 90 degree, therefore that one is y cosine theta. Correct? Which then they move it to here, y cosine theta. Okay? Now next is this triangle. This is x. If I draw a line from here to here, 90 degrees to that point, that distance will form, this one will be x cosine and that one will be x sine theta. Correct? Opposite the angle. Right? Therefore, they mark it here, x sine theta. Okay? So, V is y cosine theta minus x sine theta. Right? Next, then they have to relate u as well. U is the distance we measure from here, from this axis to there. Move down here is u. Right? Go back to the same triangle. That side is x sine, that side is x cosine. X cosine move down here, that they indicate here. Okay? Then that y come from the first triangle we talk about. That one is y cosine, so that one is y sine theta. So that pairs. Therefore, u is equal to x cosine plus y sine theta. Okay? And once we work out that form, now we're going to substitute that into that and that into that, that into that and that into that, of course. Okay? Which take us to the next page. Okay? Let's substitute for V first. Okay? That is IU, V squared dA. We have expression for V already. So we just substitute it. There. When we substitute it, then we can expand the term. It is in square, right? A minus B square. Then we have 3 terms coming out. That one is a square, that one is b square, that one is minus 2ab. Right? Okay? Nothing complex. Now, from this point on, we probably want to split the integration into 3 terms. Okay? Now, we should realize that one, the cosine theta doesn't change with dA. Therefore, I can take that one outside the integration, right? But y square has to stay, right? Because when you move dA around, y change values, okay? But theta doesn't, okay? That one is the same. Sine square can come out, that one sine cosine can come out. And then we form that integration, that term instead. Now, when we look at that form, that one is in fact Ix, right? Y squared dA is Ix. That one, x squared dA is Iy. That one, integrate xy dA is Ixy, right? Substitute for it, there. So it's not so complex after all. However, in terms of mathematics, when you have sine square, cosine square, or cosine times sine, it is hard to predict what the graph will look like. They don't like it. They rather change in the form of power 1. Okay? So, that's the next step we're going to do. We have that form. That is from the last page, not a new equation. We also have knowledge from trigonometry, if of these 3 equations. If you don't remember them, don't worry, because I have to copy down it from textbook as well. Okay? If I ask you to prove, I will supply these 3 equations. Okay? So, by the way, whatever you can guess, then we're going to substitute for the slot we want. Okay? And then it come out that form. It looked quite confusing and quite jumping the step, so I supply the arrows there. Right? Simple substitution. Okay? Now, in this form, apparently they start to look, well, it looks good. The only problem they still think is, you have the term that doesn't have sine or cosine. You have the term that have cosine and you have the term that have sine. Right? The sine is nice, it's already separate. Right? but the non-cosine side and the cosine term still mixing. So they said, well, they're going to rearrange it and then they move it that way. Basically, ix over 2 come here, iy over 2 come here, right? And then ix cosine over 2 come here, that one, and then minus iy cosine over 2 come here, that's all. Just regroup it, okay? And with that they said, well, we don't know what to do with it yet, so we're going to leave it like that for now. Oops, sorry, okay? So we're going to leave it like that. Now, for IV, the same scenario we go, right? We're going to extend the term, substitute it, expand the term. Whoops, I don't want to use that one. I forgot to change, my apology. But anyway, the idea is the same. Substitute that and then split out the integration. Okay, change y square dA into ix, x square dA into iy, and that one is ixy. Okay, it's so similar, so I'm not really showing the whole thing. Then with the same three equations we tried before, okay, then we can change it into this form. The similar step. Notice the similarity in the equation. Okay, so it's gonna follow exactly the same step. Okay, ixy is, well, not really. IUV is probably not much different either. Okay, this is the definition for IUV. This is expression for U. This is expression for V. Okay, substitute it in. There we are. Then expand the term. We have these four terms. Notice everything will be xy dA, x square dA, y square dA, and xy dA again. Okay, so we can translate it back into ix, iy, and ixy. Again, regroup them. Then we have that form, the same set of equations. Substitute it in, regroup them. Then we have that form. That one there is probably not so clear why we have to work it out. Okay. However, they realize one thing though. We go back to IU. Okay. Oh, these are the three equations we just summarized. However, notice that if you have one picture, then ix will be a constant, iy will be a constant, and ixy will be a constant that we say we know. Okay. The IU only change because the angle theta is changing. Correct? Now, we know as an engineer that if since theta is going in a circle, then it's likely that IU, IV, and IUV will go up and down like a circle. Okay? In this case, it means that IU and IV and IUV, of course, must have a maximum, must have a minimum value. Okay? But that maximum minimum value doesn't change with x, doesn't change with y, it only changes with theta. Okay? And you can guess, if we know there's a max, there's a min, then we have to find it out. And apparently they also work it out that in the end, this axis, the max and the min, is where what we call unsymmetric bending happen. Okay, then it becomes something that we have to find, and that's why we keep using symmetric cross-section area if we can. Okay, that is the equation for IU. I haven't changed anything. Now, if we want the maximum value or the minimum value, what do we do? If the function is respect to x, meaning the function change with x, then you do the function differentiation with respect to x, set equal to 0. Right? If with respect to y, then differentiation with y, then set it equal to 0. Do you know why? Why? I think you call dy dx equal to 0 and y is max or min. Why? I'm not asking do you know it, I ask do you know the reason why is it max or min there? the over dy is slope, correct? Okay. This is what we call is the max, right? Slope here is on this side is positive, correct? Slope here is negative. At the top, 0. That top is dy equal to dx, which is slope is equal to 0, right? That's the reason why it's max. Now, looking at the one that has min, right? It will be in this shape instead. Correct? At least a lot, then reduce, and then go back up. That one is min. The slope here is negative. Slope here is positive. At the bottom, slope 0. Okay? That is the reason why differentiation set equal to 0, which means slope set to 0. You will get either the max or the min. Okay? So, but this time, the function IU doesn't change with x, doesn't change with y. It changes with theta. So if we're going to differentiate it, we have to differentiate it again with respect to theta. And that will be the form. Okay? Then of course, we can differentiate that with theta. The first term doesn't have any theta, 0. Right? The second term, cosine 2 theta, take 2 out, differentiate cosine minus sine, right? That term, take 2 out, differentiate sine, you got cosine, plus cosine, but you already have minus in front, so that one becomes minus 2. And then you set that equal to 0. Notice that we have sine, we have cosine, so maybe we should solve it in terms of tangent, right? Set it equal to 0 and then move it around, then we have that form. So now if we can find out what theta gives the maximum value of IU, what you can do is substitute that theta back into the equation and you get IU, right? The IU max, of course. Okay, that one is called sometimes called maximum principal moment area moment of inertia, sometimes called major. Okay, depending on the books, of course. But they said, well, we don't have to wait until we calculate it. We could play around with the tangent meaning. Okay, so they said that let's play around with it. If that angle is 2 theta p, then that distance, because tan 2 theta p equal to that over that, right? Therefore, if you construct the triangle 90 degree here, that one should be minus IXY, correct? And that one is below here. If you know that side, that side can be found through Pythagoras, right? And in that case, it means that I can work out the expression for sine 2 theta and cosine 2 theta immediately. I don't have to wait to find theta first and substitute, because sine theta will equal to that divided by that, and cosine 2 theta will equal to that divided by that according to that expression, right? Therefore, what I can do is substitute it back into here and back into here and find immediately what is I max. Okay? And that is what we're going to do, right? That one, okay? Substitute into IU first, shall we? Then we have I max. Ooh, confusing. I have arrows. Okay? So I just change cosine 2 theta. Because this is I max now, it has to be angle, this angle here. Right? Substitute that into that and move it down here. Substitute that into that and move it down here. Notice that one minus, in the end it will be plus. The reason is, once we regroup it, it will give a simpler equation. Would it be possible? Well, we shall see. Okay? So, we agree with this form, okay? So we move on. That. Just move that form. That one times that one, don't notice the same. So square. right? That one times that one, minus and minus become plus ixy square, right? So it take this form. Notice the fraction is the same. The divisor is the same, right? So you can put them together. Once you put them together, you should realize inside the square root and outside the square root is the same thing. What is 2 over square root 2? Just square root 2, right? So it becomes this form instead. I think it's much simpler than sine cosine, don't you think? Okay? And that they lock it up as one equation for IMAC first. Okay? We want to find out at the angle of IMAX what is IUV. Okay? What is IUV? Then we just substitute it again. Right? The same theta haven't changed yet. Right there. Again, supply the arrow. Apparently, this one is nicer even, because that term and that term is the same as that term times that term, right? The same divider, that one the same with that one the same with that one, right? Meaning the first term and the second term is the same, but the first term is negative, sorry, the second term is positive. It becomes 0. At this IMAX axis, at this theta p axis. Okay? That's not the end yet, I'm afraid. Because we are talking about circle. The circle has 4 quadrants. Apparently, although when you press your calculator, it gives you only one answer for the tangent. For the arctangent, it gives you only one angle. But in fact, we are mathematicians. We know that we have that triangle axis as well for the same answer of tangent value. Right? That one will be opposite to that one, and that one will be opposite to that one. The tangent of this angle and the tangent of this angle will be the same value, but they are two different angles. Now, before we move on, notice though, this angle here and that angle there, the difference is 180 degrees, correct? Straight line. But these are 2 thetas. So theta P1 and theta P2. Theta P1 will designate to the maximum value, theta P2 minimum. The difference will be 90 degrees, correct? Because 2 theta different 180, 1 theta then 90. Meaning when you turn, when your axis U is the max, your axis V will become the min, because it's 90 degrees immediately. This is why we don't talk about IV here, we only talk about IU, because it happened at the same time. Okay? And in fact, you can rotate IU 90 degrees more to get IV anyway. Okay? Now, so in this case, we can use the same technique, finding that and then finding the 2 sine theta, and then represent for the sine and the cosine value of them. Okay? Last time, this one is negative, this one is positive. This one positive and negative, right? That's why the tangent is still remain negative, the same. The system repeats itself. Bring up the equation, substitute it, rearrange it, but this time that one turned out minus. Okay, the mean turned out minus that term. IUV is still 0. Because the system repeats itself, so I don't want to go through it again. Okay? But then that becomes summary. The axis for the principal and for the maximum principal moment of inertia and the minimum principal moment of inertia can be worked out the orientation by that theta. Okay? Don't forget, there should be 2 answers in it. Your calculator can answer only one. You must know the answer. One is major, one is minor, one is maximum, the other is minimum. And that is how you calculate plus and minus. Maximum plus, minimum minus. IUV on that x, that those two axes will be 0. Okay? Go back to the same picture we have. We already find Ix, we already find Ixy. Now the question asks, they want to find the orientation, those theta p, okay, of the principal axis, okay, and the value of them, value of the principal moment of inertia. Okay. Now we have Ix, we have Iy. In the equation we still need, we have Ix, we have Ixy, we still need Iy. Okay, and then the rest substitution. Okay, we find out Ix, we find Ixy. Okay. Now we have to find Iy. Okay, we've already find X bar already, correct? So we substitute it. This is for area 1, this is for area 2, then combine them. We have that. Okay. Then now we ready to move on to the next stage. Okay. That is the equation. We already know Ix. We now know Ixy and Iy2. Substitute, you see, just substitute it, right? The value we already have, substitute it. Work out the angle. That one. You know that this one and the other one that it doesn't give is 180 degree different, correct? So you can work out that one. Okay? Then theta can be worked out, divided, well, that's 2 theta, so 1 theta divided by 2. As simple as that. Then we move on to that. That is the answer, apparently. That is the picture. Right? Just draw. It said draw the orientation. You just turn it according to what it is. Right? Then you want to find Imax, Imin? We have the equation. What are you afraid of? Here, equation. We know Ix, we know Iy, we know Ixy. What do? Substitute for it. There, the plus is max, the minus is min. Separate it out. What's the problem? It can't be any easier. Again, I repeat myself, the difficulty in this subject is not how you calculate it. It is your concept. It is your definition. As long as you keep focusing on how you calculate it, you always get it wrong in the end. Your focus should be how you measure it. What is the distance you square? What is the main concept of it? What is the original idea? That is what you should focus. Because when you set the first thing wrong, notice that all the calculation follow it will be wrong. Because you use the wrong number for it. Okay? Make sure that you understand the definition, the concept first. Okay? Tired yet? Let's have a break then.
Okay, I'm going to go soon. However, when you look at your homework, something that you should notice, that one and that one, the triangles, Ix and Iy might not be the same. Might not be the same as this Ix. Iy of that one might not be the same as Iy. Meaning, if you calculate formulation for this one, it doesn't apply, it might not apply to that one. So you might have to prove it again if you don't have a triangle. Okay? Read the homework. If you have any doubt on how you pick up the picture, on how you calculate L1, L2, L3, L4, L2, L6, come to see me. Because I do mark it according to your picture. you got the wrong picture, you don't have any mind. Okay? So be careful. See you guys tomorrow. Have fun.